Simple linear regression's basic assumptions are linearity and common variance of y across all values of x. Some data that don't fit these assumptions can still be handled with simple linear regression, but have to be handled differently. Linearity is the most commonly violated assumption. In some instances, we can transform x or y, or both, to make a linear relation. For example, this graph shows the relation between circle area and circle radius. We know precisely the relation between area and radius, but we can't use simple linear regression to predict area from radius because the relation is curved. Fitting a simple linear regression with area and radius gives a straight line that's high in the middle and low on both ends. The r-square is high, but among other problems, the equation means that a circle of radius 0 has an area of minus 250. We know area equals pi times radius squared. Circle area plotted against squared radius is a perfect straight line. Instead of using radius as x, we can use radius squared. We still have a simple linear regression with x and y, except x is radius squared. The regression line, y equals 0 plus 3.1416x, has a zero intercept and a slope that is pi. This shows that regression can give us the value of pi and the formula for area from radius, but I don't think geometers would be impressed. Using squared radius to get a straight line relation is obvious. That's the way circles work. But the goal of transformation is a linear relation, whether it means anything or not. Y could be the number of cars passing a certain intersection, and x could be the square of the driver's ages. As long as it makes the relation straight, we don't care. A common transformation for curved relationships is the logarithm of y. The log transform has the effect of squashing the observations in the y direction. Instead of y equal 10, 20, and 30, we have log y equals 1, 1.3, and 1.5. There is no physical, mathematical, or biological justification for this transformation, except that it makes a relation linear. Also, the log base is unimportant. This shows the effect of the logarithm of circle area on the area-radius relationship. There is still a curve, but it is much less than before. Also, we can restrict the range of x to remove some of the remaining curve. In this graph, the assumption of common variance is violated. There is a flare at the higher values of x. Taking the logarithm shortens the y range and makes the assumption more palatable. The only caveat is that the regression will predict the log of y, not y itself. Any prediction must be transformed back to y, and all regression properties apply to log y. In these examples, only the x and y were transformed, but both x and y can be changed. A good example of transforming both x and y is predicting y from x in a sigmoid curve. The shape is common in height by age for people, animals, and plants. Growth is initially slow, then increases rapidly near the inflection point, and then increases more slowly or reaches an asymptote as age increases. You may be familiar with sigmoid growth as you watched in horror as your younger brother or sister suddenly reached your height. The transformation of logarithm of height and reciprocal of age produces a straight line with a negative slope. This transformation can be justified as a version of a logistic function, but mostly it just makes the relationship linear. This graph shows tree height by age. All trees are 10 years and older, so we are missing the slow growth of young trees. We still have the rapid increase near the inflection point and growth slowing at older ages. The transformation of log of height and the reciprocal of age linearizes the relationship. Base 10 logs are used in this example. The regression equation for the transformed data has an R-square of 0.87. This transformation works very well, but as with any transformation of y, the prediction is for the transformed y, such as the log of height, and not for the actual height. The prediction for log of height must be retransformed to get an actual height. Also, any regression properties apply only to the transformed variables. This is so important that it bears repeating. Any regression properties only apply to log of height and reciprocal of age. The slope and intercept are for log of height and reciprocal of age. The R-square is for the log of height. The residual sum of squares is minimized for the log of height. Since the prediction is for the log of height, the accuracy of a height prediction is decreased. We are able to use a simple linear regression, but at a price. This can be shown by finding the actual predicted height h for each tree using the transformed height prediction. The calculated residual sum of squares for height is 6,157. The regression sum of squares is the total sum of squares minus the residual. Dividing this by the total sum of squares gives an R-square estimate of 0.81 for predictions of untransformed height. This is less than the R-square of 0.87 for the log of height. There are as many possible transformations as there are people looking for a linear relation. We can combine two variables into one by multiplying or dividing. We can square root, take reciprocals, exponentials, and logs. One suggested transformation for proportion data is the arc sine of the square root of the proportion. This is purely to make the line straight. Remember, the transformations don't have to make sense. They only need to make a linear relation to use with simple linear regression.